Okay, so welcome back. Now, in the last class, I had asked you to look at why the Cauchy stress tensor is symmetric. The implication of this statement in mathematical terms is that the sigma ij is equal to sigma ji, right? And what I've done here is I've drawn a very simple set of given you a simple set of logical guidelines towards establishing this. It is not a complete proof, but it gives you more or less the whole idea. You don't have to do too much beyond this. So what I've done here is I've drawn a two-dimensional case, and this is my two-dimensional infinitesimal control volume. So this is the size. This size is okay. So I've labeled this wrong. Sorry. This is going to be delta x2. Okay, and this is delta x2. This is going to be delta x1, and there's a delta x3 that I have not drawn for you. Now we are going to take the moments about an axis going through the center of this box, and basically this is the point O, which is the midpoint of this box, and the axis is going through the plane of the paper. So what I've done is I've tried to look at what the net moment about O is. So the net moment about O will have contributions of sigma 1, 2, which is, by the way, this is acting on the positive face. So this is the stress on the positive face. This is the same stress, but this is on the negative face. So since this is on the negative face, this has to point downwards. And this, I hope you remember this, because when we are discussing the rules for the conventions for stress, we discuss this. On the top face, you have sigma 2, 1. And on the bottom you have sigma 2, 1 also, but this is again going in the other direction as the top one. And if you want to consider the moments about due to this particular stress, then you have to consider the couple, and both these stresses, sigma 1, 2 on this side and 1, 2 on this side, are creating a moment in the same direction. So there is a 2 multiplied because of contributions of both of them, and then you can just consider one of them. So sigma 1, 2. And then you have to get the force, you have to multiply it with the area. So delta x2 into delta x3. Delta x3 is into the plane of paper, so you can't see it. And then half of this arm length, which is delta x1 by 2. And this is being balanced by this moment, is being balanced by the moment that is being created by these two forces, right? So again, what I've done is I've just again we have minus 2 because of the same reason, sigma 2, 1 multiplied by these terms are all the same, and then you have to claim that the moment for this differential area has to be equal to 0. Why is that? Okay, this I am going to leave to you, so that I want to make sure you read, so I don't have to give everything out. I told you I might not give this out, but I've still gone ahead and drawn it. But I want you to argue out this for simple fluids. Now, for simple fluids, remember that there is going to be no intrinsic angular momentum for any fluid element. So this is equal to 0, which implies that sigma 1, 2 is equal to sigma 2, 1. So now you can just go ahead and repeatedly apply this to the other axes, and you can end up getting this. Okay. Now we were looking at constitutive relationships. I realized in the last class I had misspelled this, so I have just corrected it. So in your notes, this I think is some constitute relationship or something like that. It's constitutive relationship. Okay. And when we were discussing this, we had said that we have to now go and get a constitutive rule for each type of fluid. And when we look at planet Earth, the two largest set of fluids that we find is water, and then you have the atmosphere or air. And it turns out that both of these are very nice and beautiful Newtonian fluids. And so air and water are the two most common examples of Newtonian fluids. There are many other type of fluids which are not Newtonian. For example, fluids related to life. The cytoplasm in a cell is not Newtonian necessarily. Simple polymers are not Newtonian. Even a small amount of addition of a polymer to water makes it strongly non-Newtonian, and you can easily have non-Newtonian behavior, but that is going to be outside of the scope of this particular class, so we are not going to discuss that. We will confine ourselves to the topic of Newtonian fluids. Okay. So basically what we want to discuss is the stress strain rate relation for a Newtonian fluid. Okay, and so this is what is part of our course, and if you want to read about some of the other type of fluids, you have to take an advanced course, other advanced courses. Now, when it comes to Newtonian fluids, there are certain key assumptions that play a very important role in deciding this stress strain rate relationship, and these assumptions are essentially all logical assumptions. Okay, and they are the first one is that when the fluid is at rest, when fluid is at rest, the stress strain rate relationship when the fluid is at rest, the stress is given by the thermodynamic pressure. Okay? By the thermodynamic pressure. P. Okay, this is an important assumption. Now, second is that there are no preferred directions. No preferred directions in the fluid. This is also something of an observation, and I hope you remember Pascal's law, or Pascal's basically observation, where he saw that the pressure gets transmitted equally in all directions, and basically that says that some of these fluid properties are just point functions, and this is also the condition of isotropy. And in a sense, this holds true because the fluids are simple fluids. The molecules are rather simple in nature, and they do not have a particular orientation. When you start looking at the microscopic detail, the molecules are all randomly jumbled up. Okay, so there's no E there. And then the third one is that for a Newtonian fluid, and this is more specific to the Newtonian case, the stress tensor sigma ij is linearly related to the deformation rate tensor. Which is, I think I used epsilon in the last classes. So it is related to epsilon, and I'll just write KL here to keep it consistent, because we are writing in terms of the components. So this is epsilon dot KL. Now, it is not a universal truth that the Cauchy stress tensor needs to depend upon the deformation rate tensor. It can even depend upon the deformation or epsilon, not the time derivative, right? So it can also depend on that, but this is what we have seen phenomenologically, that when we work with a lot of fluids, it seems like the stress tensor is dependent linearly on this quantity. Okay, so that will play a very, very important role for us. Now, all these different assumptions are going to, let's write them down in mathematical form, because they are right now just basically words. So, if I have to look at assumptions 1 and 2 for us, and what is the implication of assumption 3, so let's say assumption 1. Okay. So, when the fluid is at rest, the pressure exerted by the fluid is the thermodynamic pressure. So, when at rest, sigma ij is given as simply minus p delta ij, where this minus p is a pressure term and delta ij, I hope you remember this is the Kronecker delta. So, delta ij is equal to 1 when I is equal to j, and delta ij is equal to 0 when I is not equal to j, right. So, at rest this holds true, which means that when at motion, when fluid is in motion, we can break up the stress here as minus p delta ij plus another component which is solely due to the flow part. Okay. When the fluid is in motion, the stress tensor would start looking like this, where this is also called the viscous stress tensor, viscous or deviatoric stress tensor. It is the part of stress that results due to the fact that the fluid is in motion. So, tau ij for a static fluid is 0. So, you only will have this particular term when the fluid is at rest. Okay. Moreover, you see one more thing is that is this the stress is a negative function, right. This is a minus p. What is a normal? So, by the way, so what happens to sigma ij at rest? Okay. Just let's quickly write this down. So, at rest, sigma 1 1 equal to sigma 2 2 equal to sigma 3 3 equal to minus p. But all other cross terms 2 1 etc., etc., I am not writing all of them, they are all equal to 0, right. So, when the fluid is at rest, every element is experiencing a negative normal pressure, normal stress, which means that the elements are in compression, right. We had this discussion before. But when you have a flow, then you will have this particular term. So, when you have flow, then these are not 0. Okay. So, these become non-zero when you have it. Okay. So, now to look at assumption 2. Okay. So, basically just a second. So, 1, 2, 3. Okay. So, wait, let's just look at assumption 3 here. What? I thought I just deleted it. Okay, 3. So, what this is saying that sigma ij is linearly related to my deformation rate tensor epsilon KL. Now, if that is true, then it's sort of obvious that my tau ij will linearly depend upon right. It should be sort of obvious from the above discussion, because when the stress tensor from here you can see that this has to be correct. So, now my tau ij is linearly related, which means that I can write my tau ij now. See, I hope you remember when we were having this discussion about vectors, that if you have one vector and another vector and they are linearly related, then the linear relationship is basically given by a linear map or a tensor. right? So for a 3 into 1 vector which maps into another 3 into 1 vector, the mapping is given by a 3 into 3 matrix. But now you have a 3 into 3 matrix is related to another 3 into 3 matrix. So this relationship that gives you this linear relationship, it can be shown that it will be given by a matrix of 9, because now each of these has 9 terms, so 9 components, so 9 into 9 are 81. So this actually ends up looking like IJKL, and this is again another tensor. Now you know probably why I wrote it as KL in the beginning and not as IJ. So this is now another tensor, and this is basically in the mathematical terminology, this is also known as a 4 tensor. It's a tensor of rank 4 and it has 81 elements. We are not in a position to discuss 4 tensors, but if you ever happen to take a course in linear algebra, which I would highly recommend, by the way, if you want to understand fluid mechanics, a course in linear algebra is extremely helpful, because you end up learning a lot about how these matrices etc. behave. And if you take a course in linear algebra, then most likely you will encounter this 4 tensors there, and they play a very, very important role in mechanics. Okay, so now my tau ij, it depends upon aijkl into epsilon kl, and this aijkl, this depends basically on the local state of the fluid. So now recall that what is epsilon KL? I hope you remember. Can you quickly recall? Where will K be? Up or down? It will be here. Okay. And this is basically equal to SKL plus RKL. So the two matrices, where this was a symmetric matrix. And this was an antisymmetric matrix. Right. Now, by the way, sigma ij is symmetric. Right. We have already established that, which means that tau ij is symmetric. Right. So you have this as a symmetric matrix that is resulting from some linear operation on a matrix that has both symmetric and antisymmetric parts. Now, since tau ij is symmetric, the components of this A matrix, aijkl tensor, multiplied by the deformation rate of the antisymmetric portion, should be such that that becomes 0. Right? Only then will you have you will be able to have a situation where they are linearly related. So now, so basically, which implies that the tau ij is such, not tau ij, aijkl is such that aijkl when multiplied by this antisymmetric part should be 0, so that you have symmetric matrices on both sides. So here you will have bijkl, some other transformation, multiplied by sk. Okay, or basically equal to some bijkl into half del uk del xl plus del u l by del. Okay, so this is how the stress tensor has to be related to the strain tensor, right? Now, when you put all of this together, our assumptions, and finally, you also need this particular assumption that there are no preferred directions in the fluid, and there is isotropy. Then the condition of isotropy means that the fluid properties are the same in all directions, and water is an obvious example of isotropic fluid, but there are many examples of non-isotropic fluids also. Fluids which have very, very long molecules, for example polymers, which are often called macromolecules or giant molecules, they are oriented, and in that case you might not have isotropy. Or you can have something like wood, and wood is composed of oriented fibers, and in that case it is not isotropic. So materials are not generally isotropic, but in this particular case they are isotropic. We are discussing only the isotropic case, that's what I mean. So it can be shown, and we are not going to show that, but it can be shown, and I will have to ask you to take this on faith, that it can be shown that a fourth order tensor that is isotropic will have the form. So my matrix BIJKL, this can be written as this matrix, del ij del kl plus mu times del ik del jl plus del il into del jk, and the other one is gamma dot del ik del I, sorry, not I have already used I, so this is JL again plus, no, this is actually a minus, this is minus del IL and del JK. Okay, and where lambda, mu, gamma are scalar quantities. Okay, so this is a general form, and this is outside of the domain of our particular class. So for us, this tau ij now simplifies down to this huge quantity, I'm just copying from my here. Del I L del J K J multiplied by this del UK del XL plus del UL by del XK. Okay, great. So now you have to carry out this huge multiplication. Okay, when you do that, and I will not, so I'm just, please do these steps yourself, please do, and when you do this, then it should simplify down and come down to this lambda times del UK del X K del ij plus mu times del ui del xj plus del uj del xi. Okay, great. So this is an important result, and I have not done it here, but you can try to do it at home by yourself and see. Do you see this particular term? This again, there is a Kronecker delta here, so it resembles the pressure term in some sense. And actually, when you expand this, it will just go ahead and club with that. And this is obviously another term, but now you have I and j, and here ji in the subscripts, right? So now, if you want to substitute to get, so our original stress tensor was sigma ij. Remember, so sigma ij is minus pi del ij plus this viscous stress tensor part, and what we were dealing with is the viscous stress tensor part for the time being. So this viscous stress tensor is this particular quantity where lambda and mu are some scalar quantities. So now my sigma ij, which was nothing but minus p delta ij plus tau ij, what does that become? So it just simply becomes minus p plus lambda delta uk by delta xk del ij plus mu times this quantity del ui del xj. Sorry, I'm just going to squeeze it, so I don't want to use another line. I'm just going to try and squeeze this last part here. Okay, I was able to do that. So sigma ij becomes this quantity. And this is the relationship that we have been after. It's our gateway to what is called the Navier-Stokes equation. We are almost there, but a little bit more remains in order to get there. But this is now also called, this is the stress strain rate constitutive relationship excuse me, constitutive relation for a Newtonian fluid. This one. Good. This in here we have these three terms. We have already seen what minus p is, and lambda here, it's also called the second coefficient of viscosity. And mu is also called the dynamic viscosity. Okay. Now, there is an important relationship that we need to find out, and that is we need to figure out how is the thermodynamic stress related to the normal stresses. Okay. So the question we are going to ask is, how is thermodynamic pressure related to the normal stresses? Okay. So to answer that, we define the mechanical stress. Okay. So let's say mechanical pressure P is equal to, and I define this as the average of sigma II, or basically, sorry, I'll also put a minus sign just to make sure, yeah, because otherwise it's okay, minus 1 by 3 sigma II, which is equal to minus 1 by 3, basically sigma 1 1 1 plus sigma 2 2 plus sigma 3 3, right? So now for a Newtonian fluid, we have just seen what these terms are going to be, right? We just derived the stress strain rate constitutive relationship for a Newtonian fluid. So let's just use that. So use the relationship we got, and then I can write my P bar as being equal to minus 1/3, and then I'll have 3 terms which will look very, very alike. I'll just go to the next page, okay, because I think I am going to roll over, I'm going to spill over in my equations. So P bar is equal to minus 1 by 3, and then there will be 3 terms which will look very similar, which obviously is just going to be this particular term, right? Minus P plus lambda term. So minus P plus lambda del UK by del XK plus, okay, so when sigma II is equal to 1, then there will be, so when these two I and j's are equal, then I also have to worry about this term, right? So this term is there, but this term is also there, and this term will now be twice of mu del u. So for sigma 1 1, this will be del u1 del x1, okay. So plus 2 times mu of del u1 del x1. And for the second case, you will again have minus plus minus P plus lambda del UK by del XK, which is basically, this is written in index notation, so it's just a sum, right? So mu del U2 by del X2, yeah. Plus again the third one. This is just repetitive, but still let's just keep it there, because otherwise it's not easy to see what's going on. So this now implies that my pressure, mechanical pressure, becomes P times minus lambda del UK by del XK minus, okay, sorry, there is another bracket here. So my P is thrice, so this 1/3 cancels with that. Lambda also is thrice, so that also cancels. But here this 2, these are all other terms, right? So these terms are not the same. So I have minus 2 by 3 of mu into all these terms. So that is just del u1 del x1 plus del u2 del x2 plus del u3 del x3. I could have also chosen another index and written it like this, but that's fine. So this, okay, now this and this are obviously the same, right? So I can just write it as minus lambda plus 2 by 3 mu del UK by del XK. Okay. So this mechanical pressure, oh sorry, what happened? Mechanical pressure becomes equal to this quantity. So this is an important. Okay, so we had asked ourselves, how is the thermodynamic pressure, which is P, related to the normal stresses, and then we had defined ourselves a mechanical pressure P bar, which is equal to minus 1/3 of this, the average of all the normal stresses. And now once we have done that, then we know that this average of the normal stresses is equal to P minus this particular quantity. Okay, and this particular quantity here is so this particular quantity is, let's maybe use capital K, and this is also called the bulk viscosity. Just a second, I just want to check how I'm doing on time. Okay, that's fine. Okay, bulk viscosity, and this is equal to lambda plus 2/3 mu. Okay, and lambda was the second coefficient of viscosity, and mu was the dynamic viscosity. I think we have written that, right? Dynamic viscosity, yeah, good. Okay, so now in general, this shows you that the thermodynamic pressure is not the same as mechanical pressure when the fluid is in motion. And what is this? So there is this additional term which sort of comes up. So your thermodynamic pressure P is my basically P bar plus lambda plus 2/3 mu. So my thermodynamic pressure is greater than the mechanical pressure, right? And this is basically, the reason this happens is because the energies that are that the normal stresses represent, and the normal stresses are representing the kind of it's basically that the mechanical pressure is basically a measure of the mechanical or energy, only the translation energy, whereas the thermodynamic pressure is a measure of the total energy, which includes translational, rotational, vibration, etc. other energies. So this bulk viscosity K, it's a measure of this transfer of energy from the translational mode to the other modes. Okay. Now, what ends up happening is that for typical flows, bulk viscosity is often neglected. Okay. Examples are monoatomic gases, where the only only energy mode is the translational mode. So when you have monoatomic gases, this K term is equal to 0, and this implies that the thermodynamic pressure and the mechanical pressure that we have defined is equal to this, are the same. But for polyatomic gases, it need not be 0. But it is often 0. It's usually very small, and let me just complete this. K is usually taken as equal to 0, which again gives us the same thing, which means that the pressure is equal to the thermodynamic pressure. And this assumption that the bulk viscosity is 0 is also known as Stokes relation. Okay. In what other case will the two be the same? When will you have this equal to this? Okay, which I'm asking you, in what other scenario will P be equal to P bar? Well, when del ux, del uk, del xk is equal to 0. And when does that happen? Well, we have already seen that there are two cases where basically it's for the incompressible fluid, the velocity divergence term is 0, that we have already seen before. So for incompressible flows, P is taken as P bar. Okay, how am I doing on time? Okay, so we're almost out. The last important point is when there's the bulk viscosity term is not always 0. There are situations where it cannot be neglected. For example, when there is a rapid expansion or contraction of the fluid, such as when the fluid passes through a shock wave, or when considering acoustic absorption, or some other scenarios, the bulk viscosity term need not always be neglected. Okay, we are getting very close to a situation called the Navier-Stokes equations, which are the key equation that we want to see in this part of the course. So I want to leave a little bit of time for discussion tomorrow, so I'll just stop here now, and we'll look at the Navier-Stokes in the next class.